early next week. Okay, so keep that in mind.
Oh, yeah.
Your first quiz is tomorrow. Let's see. I think I have notes on this. See, I even have title there for Sumatra. Did you bring me a note? You got a lab report? Well, you can either turn it in now or you can turn it in later for my step. That's your call.
If I turn it down, what grade will I get? Based
Don't
on
know.
what I have.
Depends on how the lab report looks and what you got right, what you got wrong.
Okay, I'll turn it in for a minus.
Okay. All right. So we're going to talk about quantum theory. All right. You will not see a test this week. My best guess is sometime towards the end of next week that we'll test. Depending on where it falls next week, it could very well be the first test grade of the new quarter, because I don't know when I have to post grades for the new quarter, and I won't cut it so close that there's no time to do makeup on this quarter. Okay? So, everybody good? Caught up with the title and all that? All right. So we're going to talk about the wave particle nature of light. Do you have a lab report for me? Okay. Oh, you didn't do the lab, didn't I? So you're my other one. I have a required staff meeting again tomorrow, and I have to be there till 4 o'clock. So we need to move the makeup lab until Wednesday. Will that work for you? Okay. Because I refuse to face Ms. Curry's wrath by not showing up for the staff meeting. All right, so I hate to start this with once upon a time, but it almost feels like once upon a time when I teach this theory. All right, scientists believed that electrons behaved as particles. Now, when I say particles, all right, I mean they have mass and volume. Okay? They behave like matter. They also thought that light behaved as waves. Right? And when we say waves, that means as energy. It's essentially not matter. Okay? Now, that is the way that scientists originally viewed electrons and light. Now, they've taken the history out of our curriculum. So I don't have to teach now who said what and how this evolved over time. Okay? Once upon a time, I had to teach which scientists changed the parts of this theory. Okay? That's been stripped from our curriculum. So I'm not going to bore you with which scientists changed the theory. Okay? However, I'm just going to say over time, it was discovered that electrons can behave as, I'm going to alter the view of this. I'm going to need to extend the page. It's going to get teeny tiny. All right. Over time, it was discovered that electrons can behave as both particles and waves. Now, this is pretty revolutionary for the mid-1900s. Now, why would this be revolutionary? Electrons can behave as waves. What did we just say that waves essentially were? Energy.
Oh.
Okay? So electrons behaving as energy was pretty revolutionary at this time. Now, the thought was, if electrons can behave as energy, can this be reversed? Can light, which was viewed as energy, can light be viewed as particles? Okay? It was also discovered that light can behave as both waves and particles. Now, again, pretty revolutionary for somebody to propose that light could be a particle. Light has always been energy. So how is light going to behave as a particle? How could it possibly have mass or take up a volume? Well, technically it doesn't have mass or volume, but it can behave as a particle. Okay? So, in summary, scientists have proposed that both electrons and light can act as particles and waves. Now, we're going to demonstrate, or I'm going to explain this through two theories later, probably tomorrow. We might get to start it today, which is the photoelectric effect and neon lights. All right? Neon lights, most of you are very familiar with. The photoelectric effect is just sort of out there. All right, everybody caught up? Now, because we are talking about electrons behaving as waves, we have to know something about waves. Do y'all remember it from middle school? Frequency, wavelength, how they're related to each other? How to tell the colors on an electromagnetic spectrum, what an electromagnetic spectrum is.
Oh, yeah.
You remember that?
A little.
You being sarcastic?
No, I remember of it. I did not remember.
UV rays and stuff.
Yeah. Okay. What is electromagnetic radiation? Any form of energy that travels through space in wave-like let's say with, instead of in, sounds better, with wave-like behavior. Now, if you want to abbreviate it, you can abbreviate it EMR for short, because you're going to get tired of writing out electromagnetic radiation, I'm sure. Okay, so you can abbreviate it EMR if you want. But any form of energy that travels through space with wave-like behavior. Now, I would be willing to bet that y'all can give me lots of examples of this. And we'll write them down on the next board. So wait till we get there and I'll let you yell them out and I'll write them down. And I'll pretend for a moment I take shorthand. Rid of all that. Huh, I didn't know I had that. Maybe I should put that in. Pop that out of there. Maybe I should put that in Canvas. Crapola.
I just like how like I'm doing it. Like, you know, you try to write it. It's like your things are like it's like when I eat and get food in there, like I can't get it out. So,
Is that one different? That one looks different. Take both of those. Distracted myself, sorry. Just thinking about what I could put in Canvas to help y'all review. All right, I'm back. All right, so. That's not what I meant, stupid board. Over there. All right. So, what are some examples we can write down? No.
Okay.
Now, generically, a lot of people refer to electromagnetic radiation as light. It's not technically a way we should refer to it as. So I'm not going to write light as an example because it needs something else. It needs another word in front of it. I thought Zaya said one a minute ago. UV works. And UV, for those of you who don't know, in case there's anybody who doesn't, is the shorthand for ultraviolet. What? Sure. All right, what else? What else? Precious, hush. Contribute to the discussion. What else? Give me another form. I thought I heard one.
oh, I just said it EMR. That's
No, I thought I heard something else. What'd you say? Micro. Yes. That's all we got out there? It's okay to say something stupid. You'd be amazed at some of the stuff I hear throughout the day.
You're gonna be like,
Won't be the first time my brain said dang inside. It's very rare that I will laugh at an answer. I even held a straight face one time when somebody asked me what a yatchet was. Okay? I promise you, it's very rare I can't hold a straight face. Doesn't matter what you yell out. Okay. It was a senior. She's like, I ain't got on one of them any day anyways. So,
Is a sound wave an example of it?
yes, it can be. All right. I want you to be a little more specific. What kind of sound waves might we hear? Got that. What do y'all listen to?
Music.
Okay, so what kind of sound waves do you hear? Yes. There you go. They're called radio waves. Some people still do.
No, it's embarrassing.
It's embarrassing to listen to the radio. Is that like having poor pods instead of AirPods? All right, we got anything else? All right, find your orange sheets, your stapled ones. I don't have the rest of my life for y'all to come up with these.
Radio waves, microwave.
We did. Do you have a lab report?
X-ray.
Who else came in besides you? Xavier came in and Zaria. So it's just you. Yes. Yeah, on my desk. So turn to the very back page. That's where we're going to be all day.
Infrared.
All right, infrared.
X-ray.
Now, infrared, you can abbreviate IR. X-ray. What else? All right, that's the one that I wanted from you, Franklin. Thank you. Your pleasure. All about saying that to me. Because everybody else I asked didn't have what or said. They turned it in late.
What are they?
All right, so visible light. Have we got them all now? All right, so keep that handy. We're going to use it again. All right, so what two properties identify those types of EMR? How do you know which one's visible light, which one's gamma? For example, the only one out of those that we can see is visible light. We can't see microwaves. We can watch the microwaves spin around all day long. We can't see the microwaves. We can't see UVA and UVB. I mean, you don't see a bunch of us out there sunning ourselves in the summer, dancing around going, ooh, let me avoid that one so I don't get skin cancer. Okay? So we can't see those. Yeah, no, a bunch of dumb white people sitting out there trying to get brown. All right? That's why I'm pale. I have better sense. Now, so how do we discern which one? There you go, wavelength, and what else? It's not on there. All right, wavelength is one. Now, some spectrums have it. Ours just doesn't, because the state wants you to know the relationship between this and the opposite.
Frequency.
There you go.
Oh my gosh, really?
Yeah. Okay. Now, if you remember this from middle school, or you had physical science, you would have also learned amplitude. Amplitude is not part of our curriculum, so we will not be learning amplitude. Okay? Amplitude is about loudness. If you take band, you may have learned about amplitude, how high or tall the wave is. That talks about how loud something is. We're not going to do that because it's not part of our curriculum. Wavelength and frequency are. Okay? Everybody got it? All right, so we're going to start with what is the electromagnetic spectrum? No, I don't expect you to draw that. All right, so the electromagnetic spectrum just shows all types of EMR arranged by their wavelength. Okay? So, if I was to give you a question and say, which one has the longest wavelength, okay, you would be able to look at this and see who has the longest wavelength, right? Because on the chart, see how it has longer wavelength, shorter wavelength? See how it's marked on the chart?
Yes.
Okay. So if I said which type of EMR has the longest wavelength, who would have the longest wavelength?
Radio wave.
Radio waves. If I said which color had the longest wavelength, which color would have the longest wavelength?
Red.
Okay. Now, visible light is only in this little itty bitty range right here. All right. That's all that visible light is that little itty bitty red range. Okay. Out of this giant spectrum, we only see this little narrow range. Now, they've pulled it out at the bottom to show you the colors. And we're going to spend more time with that here in a little bit. All right. But the longest wavelength is red. The shortest wavelength is violet. Okay? Everybody good with how to read short and long wavelength? All right. Because remember, I won't tell you to go back and look at this when you need it. You have to know to look for it. All right. So what is wavelength? Now, I'll tell you on the quiz tomorrow that some of this is going to require you to write the definitions out. It's all free response. Some of you are going to be stunned tomorrow when you see the quiz. So I'm trying to give you a little heads up before I hand you the paper and you go, are you kidding, Miss Wall? The first is, no, I'm not kidding. Okay. If I say, what is the definition for wavelength? I expect you to be able to tell me. And it is not the length of a wave. If you write that, it's minus 10. Okay.
This is
Getting warmer. Okay. Wavelength is the distance between two corresponding points on adjacent waves.
Minus 10.
Right.
For some of you, it's going to be bad. The good news is it's on the end of the quarter, and hopefully it won't have much impact on your grade. For those of you whose quiz grades are already bad, it will have very little impact. For those of you whose quiz grades are really good and you flub it up badly, you'll see more impact.
How much impact?
Depends on how badly you flub it up.
Wait, Miss Wall, how many questions is it?
10.
And are we gonna need to know all these definitions?
You will need to know some of these definitions, yes.
Oh, how many of them?
Several.
Several.
Hello, Ms. Hudgens. I told you, this unit is completely different than the last. So there's no math. Many of you who enjoyed the math will hate this unit.
I already know.
I'm so sorry. Now, so if we look at a wave, okay? First of all, what makes up a wave?
Crest and trough.
Very good. Look at that old vocabulary coming back. What's a crest?
The tallest.
The highest point on the wave. All right, so this is a crest.
All are different.
Yeah, and this is a trough. Okay, the lowest point on the wave. All right, the trough is the lowest point, and the crest is the highest point. Okay, that is not really my area to teach, but I'm just throwing it out there because you should know that. Now, in order to find the wavelength, all right, corresponding points. You may pick any point on the wave, but it has to be the same point on the next wave because it says adjacent waves. Adjacent means side by side, okay? So if I pick this crest on this wave, I have to pick the crest on the next wave. So this would be one wavelength. Now, did I have to go from a crest to a crest? No. I could have said a trough to a trough. That's the wavelength.
And it should be
Now.
the same thing.
Again, I don't have to do that either. I could have said, I'm picking this point going down on this wave. If I pick the down point on this wave, I have to do what on the next wave? The down point on the next wave. So the down point there. That would be a wavelength. Okay? It doesn't matter what you pick as long as it's the same point on the next wave, which is why the definition is the corresponding point on the adjacent wave. Same point, next wave. Does that make sense? I'm going to go with a yes on that. Now, the units. Let's see if I put it on another slide or if it goes on this one. Yep, it goes on this one. All right, the units, because we're going to calculate. This is where our only calculation comes from. The units for this, it's a length, right? Anybody remember the SI unit for length? Meters. Good, Xavier. All right. We're going to use meters. I'm going to put nanometers here because we're going to learn about nanometers in a little bit. All right. And the symbol. I knew there was something else I wanted. The symbol we're going to use will be an upside down Y. It's a Greek symbol. And it is lambda. Lambda. Like the sheep.
What's that?
There you go. Bah.
What does that mean?
What? It's a Greek letter. It's just the letter in the Greek alphabet.
So the symbol that represents what we're talking about, wavelength.
Yep, it represents wavelength.
Franco, hush.
All right, you with me? Zaria's going to fall out of her chair with boredom. We ain't even got to the boring part yet. What did we do for the photoelectric effect?
Wait, this isn't the boring part?
No.
We're going to learn about the other boring part today?
Maybe. All right, frequency. Frequency is the number of waves that pass a given point in a given amount of time. So this one comes with a formula. So this one is the number of waves over the time. All right, so let's just say that this whole wave takes place in 1 second. Now, if you're going to calculate this, you have to draw the wave exactly as I have it on the board, or your calculation is going to be jacked up. How many crests do I have? 3. How many troughs do I have? 3. So if you draw it, make sure it's exactly like mine, or it will make no sense when you go back in your notes. So, what makes up a wave again? Nope, I'm just asking what makes up a complete wave.
Crest and trough.
Okay, so this is one wave. Okay, so how many waves do I have on the board?
3.
Okay, so when I look at this, I have 3 waves over what is my time? 1 second. Now, as long as the crests and the troughs match, when you look at my wave, how many crests do I have? How many troughs do I have?
3.
As long as they match, you just have to count the crest. For those of you who are like, I don't know how she got 3 waves. As long as these match, 3 and 3, just count your crests. 1, 2, 3 crests. That's how we get the waves. And what's the time at the end? So 3 over 1. The frequency is 3. Now, the unit. The unit is hertz. It's abbreviated Hz, so we're going to put hertz on it. It means 1 cycle per second. All right, 1 cycle per second. Now, the last thing is the symbol, because we're going to calculate here in a minute. The symbol it's the Greek letter nu, and it's an italicized V. Now, I cannot italicize when I write on the board, so it just looks like a normal V. When I type it on the test, I can italicize it, and it will be italicized on the test. I've tried slanting it over the years, and people ask me, what the heck is that, Miss Wall? So I just write it as a V now. It's just V. But it'll be italicized on the test. Okay? Questions? Anybody have a question?
Yeah.
About the difference between frequency and wavelength?
Oh, wait.
Mm-hmm.
Wait, so NU dash V, like it all goes together?
NU is the name for V. It's
Oh.
pronounced nu. That's the name. Like the upside down Y was called lambda, V is called nu. Sort of like if I write that, do you know what that's called? It's a Greek letter, people.
Oh, Greek fish.
It's called alpha.
At least I was close.
Should have known better.
You did. You know better.
I knew better than to put it there. All right, so how are frequency and wavelength related to each other? How are they related?
They're both maybe different.
The higher the frequency, the smaller the wavelength.
That is correct.
I'm on a roll today.
You are.
Maybe this quiz isn't going to be that bad after all.
Let me make that a little smaller. I'm not sure I can make both of them fit. All right, I've tried to draw them at roughly the same amplitude or the same height so that that's not changing. All right, so what can you tell me about the top one? All right, and the number of waves don't really matter. It's irrelevant. What can you tell me about the wavelength here?
It's very big.
Long.
Okay, so it has a very long wavelength. All right, so if it has a long wavelength, what will that do to frequency? Have a big frequency or a very small frequency?
Small.
Okay, so it has a very low frequency. Now, how can we calculate the frequency for those people who are like, I have no idea what they mean by frequency? Frequency is the number of waves. How many waves are in that top picture?
2.
2, okay? We know it's a low frequency because there are 2 waves. That's how we know it's a low frequency. There are only 2 waves in that picture, okay? It's a long wavelength, small frequency. Now, look at the bottom picture. What can you tell me about this wavelength? Okay, it has a short wavelength. Okay, tell me about its frequency. Okay, it has a high frequency. All right, why would it have a high frequency? All right, what can you tell me about its number of waves? Or is it a large number of waves or a low number of waves? Large number. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 waves this time. That's why it has a high frequency. Okay? So when the waves are short, wavelengths are short, you have a high frequency. All right? Does that make sense to anybody besides me? I got some nodding heads out there. So, what's the math word that we can use to describe that relationship? They're what of each other? If you have a long, okay, opposites is good. All right.
Inverse.
What?
Inverse.
I like that word so much. All right, so opposites.
Again.
All right. So we're going to call them inversely proportional.
Inversely.
Did I spell it wrong? Yeah, I did. I left out my R. There. Inversely proportional. All right, so they're inversely proportional. Now, what does it mean to say inversely proportional? Because we're going to use this the rest of the semester. If one increases, the other what? Decreases. Okay, so if one increases, the other decreases. That's what it means to be inversely proportional. Everybody with me on that? So if wavelength gets bigger, the frequency has to do what? Get smaller. Put your phone up, Precious. I want to play on mine too. I want to go read my book, but instead I'm teaching this.
What are you reading?
Something called adrenaline.
You should get Audible. They'll read the book for you.
All right. Everybody there? All right. So, since I've used up all my space, let me put in a page. The equation is our only math formula for the next roughly 4 weeks. Okay? So here's our formula. C equals lambda nu.
Whoa.
That's it. It's our only math formula. Now, C is a constant. It is the same C that's in Einstein's equation, E equals mc squared. If you remember that from back in middle school or wherever you would have seen it. Anybody remember what it says? What the C stands for? Nobody? It's the speed of light. Okay? C equals the speed of light. And it's a constant. It's 3.00 times 10 to the 8 meters per second. There's a group in France that have moved a particle in the particle accelerator faster than the speed of light. But other than that, nothing's moved faster than the speed of light. All right, what have we said that lambda stands for? Huh? Say what?
The particle accelerator is a real thing?
Yeah.
Like
In
from
France.
Flash?
Yeah.
Well, I'm sure the Flash is probably not, but the particle accelerator in France is. What's
Wait.
that stand for again?
Harrison Wells?
Lambda.
Yes, that's lambda, but what quantity is it? Wavelength. Okay. So that's wavelength. And this is what? That's frequency. Now, in order to solve for this, okay, wavelength must be in meters. Okay? That's going to be the issue we're going to have. It's got to be in meters. So we're going to have to change nanometers into meters. So I'm going to go ahead and tell you that 1 meter is equal to 1 times 10 to the 9th nanometers. We're going to have to use that. You're going to have to put this in your memory. So there's 2 numbers on this page you have to learn. The other one up there is the speed of light. We got it? Ready? All right, I'll let you write down the problem. And then we're going to calculate frequency and determine the color of the light. Only it should say what is the color. Apparently I was saving some space there. What color and frequency of light with a wavelength of 450 nanometers? Let me go mark my tardy people here while y'all are writing that down. Only with some Michaela today.
You said nanometers, how many meters?
Say what now? All right. So, what are we going to do first? What do we need? Tell me something you know. Anything. Y'all look so excited to be here. Okay, we know the wavelength. Okay. So, what are we going to find? Okay, we're going to find color and frequency. What should we find first?
The frequency.
Which one? Let's not do both. Pick one. Frequency, okay? And Lana said frequency. We're going to go with that. All right, so what do we need? What do we need?
Number of waves.
How about we use the formula? Thought that might be easier.
Them
Okay.
symbols, I don't like them.
I can't help that you don't like them. That's the formula. If we were in physical science, they would have changed it to V equals this. Okay? They completely altered the equation. But y'all are not in physical science, so we're not using the fake equation. All right, so what does C stand for? Speed of light. What is the speed of light? All right, so we're putting 3.00 times 10 to the 8th in for C. It's a constant. You have to learn the constant. It never changes. That is C. Okay? What are we looking for? What Elena say? Frequency. Well, so what letter is frequency?
U.
The who? You don't have a U.
A V.
A V. Okay, so we're looking for the V. Okay, so we know the constant. We know we're looking for V. So we're looking to plug in the what? The wavelength. So we need to plug in the 450. Here's the rub. This is meters over seconds. And this is what?
Nanometer.
Do the units match?
No.
You got to make a match. Okay? So, I'm just going to go right back here to this empty board. 450 nanometers have to be changed to what? Meters. Because they have to match. That's all you have to do is change the nanometers into meters. So just like back when we did King Henry, who's bigger, a meter or a nanometer? A meter. If you don't know about nanometers, nano is the study of very small things. All right, there's a whole department at Forsyth Tech that's just about the study of nanometers, or nanoscience is the study of very small things. You can get a whole degree program at Forsyth Tech in nanoscience.
What are you
All
going
right.
to do with that?
I don't know. There's lots of jobs for it. Go up there and ask them. All right. I've never been interested enough to find out. All right. Now, since meters is bigger, we put a 1 there. And that means if we go back, what did I tell you we're going to have to learn nano is equal to? So we're going to put 1 times 10 to the 9th here. you're going to use your trusty calculator and divide
4.5
to the negative 7. All right, so that's our wavelength. So where are we going to put it?
for the y.
For the upside down one.
lambda.
For the lambda. That's an even better answer. Okay? Because Franco's making me symbols over there, like he's doing YMCA or something. It does look like a lambda. It's a very good lambda. Okay, so back over here, we're going to put 4.5 times 10 to the negative 7. Now, I'll even take the unit out. You're sitting in math class. This is like middle school math. All you have to do is solve for V. What do you do?
Divide by 4.5 times 10 to -7.
Exactly. That cancels on this side, leaving you with V. So you divide on this side by 4.5 times 10 to the negative 7th. And I don't need two V's, or 2 equals with my V. All right, so did anybody get me an answer?
Uh, 6.666.
How about we round to 6.67 so nobody gets all bent out of shape?
To the 14.
All right, and what unit do we put on our frequency? Frequency has what units?
Hertz.
I was going back, but whoops, there. Frequency has what?
Hertz.
Hertz. Frequency has a hertz. Okay? Questions about how to find frequency. Now, we got to find color. How do we find color? It's the only thing we've done today that has color on it. Okay. So I got lots of people with the orange sheets. That's fabulous. What is the orange sheet read by? Frequency or wavelength? Wavelength, right? So, if you look here, wavelengths. These are your meters right here, right? Okay, you had 4.5 times 10 to the negative 7. This is a number line. Where does 4.5 sit on the number line? Now, notice it's backwards. So you got 4.0 to 4.2, 4.2 to 4.9. So, 4.5 sits right there between the 4.2 and the 4.9. So what color would it be?
Blue.
It would be blue. Everybody see how we did that? Now, did we have to find frequency before we did the color?
No.
No, you could have done color first, which is why I asked which one did you want to do first. It did not matter which one you chose to do first. Is everybody okay with that? Yeah? All right. I do. You do. Y'all do that. Yeah, go right ahead. Where we at? Done? Need more time? A couple more seconds. Got it, Samantha? Do I have anything similar to what anybody else has?
I got 4.6.
I don't know.
Exactly that.
You have exactly that?
Is this what I'm supposed to
It'll be something that's on the quiz, yes, but it won't be 10 questions. Be one. All the other stuff we've done so far today. You said 6.5 to 6.25. That's why you're getting a slightly different answer.
Oh.
Anybody else? Huh? Because you got 11 there and it's -7. Punch that in the calculator and we see what you did there. There you go. That's fine. 625 divide 1 second. So say times 10. That's what's giving you that weird answer. Okay? That's what's doing it. Because your work is right. You're just punching it in the calculator wrong. Anybody else got a calculator issue getting strange numbers? All right. We feel okay about that? Probably going the wrong direction. All right. All right, if you will, come pick up your clicker card off the table. I'm going to do a few questions just to break the monotony in practice, and then we'll go back to the photoelectric effects.
Did we just get any one?
Oh, you got to get yours.
Oh,
Guys, you have to get the one that your number is assigned to on the board. Okay? There's a number on the board. Get the one that goes with your name and number. Okay?
Oh, okay.
So, Zaya, you are 3. Zyra's 2. So 6 should be Michaela. Yes. All right. Now, I'm assuming that most of you have played this before, but maybe not. So I'm going to use Xavier, who has 22. All right. So you look at the cards. There are A, B, C, and D on the cards. If you've never done this before. So if you think the answer is A has to be pointing up. All right. If you think the answer is D, then D has to be pointing up. All right. Hold your card up. It's a QR code reader. So my phone will scan the code. It will show your name over here on the right-hand column. It'll turn blue. Blue just means my phone read your answer. It does not say whether your answer is right or wrong. It just says it read. So you can stop holding the card in the air. Now, secondly, if your finger is a little bit in the black, like mine is right there, it will not read the code. Okay? Your fingers have to be out of the black area entirely for mine to pick up the code. Got it? It's that simple. We're just going to do a few questions, make sure we're all on the same page, and then we're going to move on. All right, so. The only thing I don't like about this is I can't make exponents and subscripts. So like on this one, you see how the question has like 10 and then -7 and 10 and -15 and 14. Those are your exponents, okay? And I'll give you a moment to calculate since that's when you got to calculate. You ready?
No.
Let me give another minute or so I can do most of it in one pass instead of doing it 3 and 4 times. All right, ready? Yeah. Okay. All right, so we got most of us right. We got a couple of people with the wrong answer, and that's because the 6.5 times 10 to the negative 7th is the what? That's the wavelength. Okay, so you got to take this and you've got to do your 3.00 times 10 to the 8th equals 6.5 times 10 to the negative 7th times V, divide, and when you divide, you get that answer. Okay? All right. So, all right. Microwaves is the right answer. You're looking for the one closest to what? Radio waves? Yep, closest to radio waves, which would be microwaves. Okay? So, if we ever get one that's all the way correct, that's something on the board. Which of these is not an example of EMR? We can't get this one right. I don't know what's wrong with us. I don't see that very often.
Real.
Yeah,
Dang.
it's very rare I get that.
What?
Confetti on the board, 100%. I can count on one hand the number of times I've seen that.
Oh, I'm done.
I would hope I'd see it on this one too.
Wait.
Y'all are gonna be shocked.
Yes,
Bruh.
sir.
Yeah.
What do we know about frequency and wavelength?
The shorter the wavelength, the higher the frequency.
They're opposites, right? So, on your chart, it said long this way and short this way, right? Okay. So, if it's long wavelength this way and short wavelength this way, that means high frequency and low frequency. So when I say which one has the highest frequency, you're looking for the shortest wavelength. So the one that has the shortest wavelength will be purple. Okay, they're opposites of each other. All right, we can't do that one yet. We can't do that one yet. Let's do this one. We can do that one. I'm going to show you all a shortcut in a minute. All right, 5.5. All right, all you had to do was take the 550.
Oh, I'm dumb.
Now, most of y'all converted, which is fine, and probably got 5.5 times 10 to the negative 7th. It's always going to be times 10 to the negative 7th. Okay, when you look at the numbers on your chart, they all have the same exponent. All you have to do is put 5.5, move the decimal. Okay, they're all something that has a decimal after the first number, so 5.5. So on your graph, on your orange sheet, where does 5.5 fall on the number line? What color is 5.5? Okay, see how I did that without doing a calculation? You can do the same thing. All right, I think I might have one more question that we have. Yep. Last one, and I better have 100% here.
Oh,
They're opposites. They're inversely proportional. All right, if you will, put your cards back on my desk. That's good. I'm glad to hear that. Because the other two questions I have, we haven't done yet, so we can't do those.
Precious.
Oh no. This is the boring part.
Yeah, yes, it was boring before. Now it's going to get worse. All right, so if you will, find your notes again. All right, we're done with your orange sheets. We're going to talk about the photoelectric effect for a little bit before you leave. All right, the photoelectric effect is one of the examples to illustrate how light can behave as a particle and away. Okay? Neon lights are the second. We will not talk about that at all today. We will not finish the photoelectric effect. We're just going to start. All right, so for Sumatra who likes titles,
It's gonna be.
this page might no further than this page. So. All right, so what is the photoelectric effect?
Wait, what was that?
Photoelectric effect. All right, so what is the photoelectric effect? The photoelectric effect refers to the emission of electrons from a metal when light shines on it. Okay, and I did these notes probably, I don't know, 5-6 years ago at this point, because the state put this back in the curriculum, and I was like, you have got to be kidding me. So I was trying to figure out what I should teach and what I shouldn't teach out of the unit, and I still don't know to this day if I'm too much or too little, but this is what I chose out of the topic. Might be too much, might be too little. But I never get to see the state test, so I still don't know. All right, but it refers to the emission of electrons from a metal when light shines on. So imagine aluminum foil at the house. And you shine a flashlight on the metal, on the aluminum foil. And an electron is ejected from the metal. All right, emission means to give off. For those of you who don't know that, that's what emission means. So I'll just write give off right there. Okay? So the metal is going to give off electrons when light shines on it. So, does that seem like a normal, natural phenomenon to you? To shine a flashlight on aluminum foil, and the aluminum foil gives off electrons? It's not. Okay? Now, so the question becomes, what causes this? All right, why does it happen? So the mystery of the photoelectric effect is involved in the frequency of light. All right, do all lights cause this? Will the light bulbs in here shine on aluminum foil and cause electrons to be ejected or emitted? Can you use a flashlight at home? Your desk lamp? Your cell phone flashlight? Does it have to be a particular frequency of light? Does it have to be high frequency? Does it have to be low frequency? Does the frequency even matter? Okay? What do y'all think? Does it matter? I know you don't care, but does it matter? All right, I got to vote for no. What do you think, James? Yes. It does matter. Okay? The frequency of light does matter. Not every frequency of light is going to allow electrons to be emitted or ejected from aluminum foil. Okay? I can sit in my kitchen, turn the lights on, and electrons are not going to be ejected from the aluminum foil. Okay? Now, the problem is, wave theory of that time said that any light would eject electrons. You could use your flashlights on your cell phones. An electron should be ejected, according to modern day wave theory at that time. They had no reason to say, oh, electrons are not going to be given off. So there had to be some other theory that would work. So scientists had to figure out what that theory was. It's not time yet, 5 minutes. I know, it's a long time. All right, we caught up? So, that's not what I meant to do. Get back down there. Now, so if wave theory doesn't explain it, what is going to explain it? Well, scientists found out that only light above a certain frequency knocks electrons loose or emits them, which should make sense. Not every light is going to cause electrons to be ejected from a metal. Okay? Your lights in your house are not going to do that. But scientists need a way to explain that. Why does one light bulb knock electrons out of a metal, but not other lights? They have no working theory at this point. Okay? And again, the history part of it, and most of that has been taken out of the curriculum. But I'm not going to leave it all out. I'm going to tell you who fixed it. We're going to talk about a couple scientists. There's a German physicist by the name of Max Planck who came along and fixed it, okay, or explained it, I should say. Because they knew it happened, they just didn't know why. All right, and that's where I'm going to end things. All right, German physicist Max Planck, all right, explained or theorized that electromagnetic energy is not released continuously, but in small packets called quanta. Now, that is the reason that all of this stuff we're talking about over the next few days is called what theory? Quantum theory. Okay, it's all based on the name that Max Planck gave it when we talk about energy. Okay, Max Planck proposed that electromagnetic energy is not released continuously, but in small packets called quanta. And we'll keep going with that tomorrow. For homework, hand out the sheet, and I will tell you what numbers as soon as I get back around, so I can tell you which numbers to do. It's prep work for the quiz. You will see tomorrow.
So this will help us study for the week.
You should, yes. Easy on the calculator. You need to know the wisdom. This will be the good thing about not needing calculators beyond the quiz tomorrow. Y'all can abuse them less.
Can I get a sheet?
Yeah, I thought I put one on your desk, but maybe I didn't. Did I not pass an extra one down, Raylina and Jania's row? I thought I did 3, but I must not have counted right. That's what I meant to do. All right. 1 through 11, 23, and 24 are what y'all are doing tonight. Everybody got it? Have a great